If you look at any topographical map with contour lines and at least one water stream, you'll begin to notice that in every single map, the contour lines are always perpendicular to the water streams. But why? Why don't they flow with the lines? Or why doesn't the water flow at a 45-degree angle or something? To explain this, we need to start off with directional derivatives in the plane. We'll be using a lot of the chain rule in this video. We're going to be using a lot of the chain rule here, which if you don't know, you should know. It just says that f is a function of x and y, and x and y are functions of t. Then df dt is this. I mean, it's really easy to memorize because it's really symmetric. So, alright, so let's say that there is a function f of x and y that is defined in a region R in the xy plane that contains this point PO. And any line through PO, let's say this one, can be parameterized with this set of equations, where S is obviously the arc length parameter, and ux and uy are the components of this unit vector u. We can actually find the rate of change of f with respect to the arc length parameter in the direction of u. The definition of a directional derivative with respect to arc length, you might notice, takes a really similar form to the definition of the derivative of a single variable function. We use this notation for a directional derivative. This is df ds with u and PO. So in the direction of u at PO. And another, notation for a directional derivative would be this. This is just the same thing. These two are the same thing. And using this definition for a directional derivative, we can actually derive the definitions of partial derivatives. Here on the left we have the definition of a partial, and a partial derivative is just a directional derivative. Let's say a partial with respect to x. So in this partial, we're keeping y constant. So this directional derivative would just be the derivative in the plane y equals a for, a just being a real number. So we're keeping y constant. And in the plane y equals a, the unit vector that we're differentiating towards, or in the direction of, is obviously 1, 0, because this is the unit vector that's parallel to y equals a in the plane, the xy plane. So ux here is going to be 1, and since the x component is already 1, we can just replace s with h. H doesn't have to be arc length parameter, but h is basically an arc length parameter here because ux is 1. So this becomes xo plus h, and uy is 0, so this just becomes yo, and we can replace this with h also because it's basically the arc length parameter. Alright, anyway, sorry for that tangent. Main thing to get at here is that this is the definition of the directional derivative, and I suggest that you focus on this particular on the left side, because if you expand df ds using the chain rule, you get this right side, which is the chain rule. And what you'll notice is that the right side can be expressed as a dot product. I actually went on this in the last video. Please watch that if you haven't. But this right vector here can actually be just rewritten as ux uy, which is this ux uy is literally just u hat. So this is just the definition of a vector. And this is where we define a new term. It may just seem to make this computation or dot product easier, but actually it's very useful. And that is called the gradient vector. This is called the gradient vector. It's notated as this, notated. You can read it as grad f or del f or gradient of f. It's just this is the gradient vector of a function f. In general, if f is a function of an n amount of variables, grad f will be a vector with n vector components, with each of the components being a partial derivative with each of the variables. Using this and this, we can replace both of these with this dot product now. So finally, we get a really simple way to compute. Directional derivatives with this dot product instead of having to do all that freaking limit stuff. Actually, this definition only applies when u is a unit vector. If u is not a unit vector, then we rewrite it as this. This is the general one, but since for a unit vector u, this is just 1, we can just keep with this. But for simplicity, we'll use unit vectors. And using properties of the dot product of two vectors, we can also find out that the directional derivative can be expressed as this, where theta is obviously the angle between u hat and grad f. This reveals very, very important properties regarding rate of change. The maximum value of the cosine function is 1. So, first of all, we know that f increases most rapidly, or the directional derivative is the most, when norm of grad f is the most. And we also know that the maximum of the cosine function is 1. So, we can say that the directional derivative is at its max when the cosine function is 1. Or cos theta is 1 when theta is not 1, what the hell? 0. So the directional derivative is always greatest in the direction of grad f. And also, it's at its minimum when cosine theta is -1, since -1 is the minimum of the cosine function. Since that is when cos theta is -1, then that means theta is pi. So when theta is pi, that means u is faces in the opposite direction of grad f. So now we can say that f increases most when we're taking the derivative in the direction of grad f, and decreases most in the direction of minus grad f. This is a very, very important result to show why the water streamlines are perpendicular. Alright, so let's say that the function, or not the function, the equation f equals c for c in R represents a level curve of f in its domain. So say this is the graph of f equals c. So now let R of s be the vector function that represents this level curve, that represents every point on the level curve. If we want to find the directional derivative of this function, or in the direction of a unit vector, we realize that f is a function of x and y, which are both functions of s, so you'll probably know where this is going. If we take the derivative of this equation that represents the level curve with respect to s, we get df ds is this, which is equal to 0, because derivative of constant is 0. And this chain rule right here looks very familiar. This chain rule can obviously be turned into a dot product, and this over here is just the gradient vector, and this over here is just the derivative of r with respect to s, or in other words, grad f dot r prime is 0. Well, what is this saying? What is this saying? This is saying that on any point on this curve, the tangent vector r prime. So let's say we're over here, and this is r prime. This is saying, all right, let me do this. We can rewrite this dot product as this, and assuming that grad f and r prime are non-zero, the only way for this dot product to be zero were if cos theta were 0. And the only time cosine theta is 0 is when theta is pi on 2, which means they're perpendicular. So this is saying that grad f is always perpendicular to the tangent vector to the curve. Or in other words, grad f is always perpendicular to the curve, to any level curve in any function, no matter what. And here we make the final step. Remember when I said the directional derivative is always greatest when the direction is grad f, and least when the direction is minus grad f. So in other words, the function is changing the most in the direction, or when the direction is parallel to grad f. Alright, here I've drawn some more level curves of this function f. So I'm just going to draw the gradients. So imagine this was like a figure with continuous level curves and continuous gradient vectors showing. So I'm going to try to draw that. So it would be something like this, would be the mapping of every single gradient vector possible. What does this remind you of? It should remind you of the topographical maps with the streams. The streams are always, think of the contour lines as the level curves, which they literally are. They're the level curves. And so the water is always perpendicular to the level curve. The water is always going in the path of the gradient vector, which means the water is always going down the hill in the fastest way possible, which it should naturally do. And then that explains why all these water streams are perpendicular, going perpendicular to the contour lines, because they want to go down the hill as fast as possible. And in this video, we've just shown why it's the fastest way possible to get down the hill. Because remember, the directional derivative is greatest and least when you're going along the gradient vector. So I hope you guys enjoyed this video. If you liked the video, press the like button. If you didn't like the video, press the subscribe button. And yeah, bye.